All right, so in this video I want to talk about memory, bytes, how everything is really made up out of bytes, and how we can sort of relate to this, how we can use this. And in some ways I want for this to kind of demystify a little bit what structs are, unions, and so on. And maybe make it a little bit clearer sort of what we're dealing with. So for this purpose, I made this very simple thing here. It's really just showing the sizes of different things. And the important part is not necessarily the sizes here, right? But to realize that the relationship between these sizes is a lot simpler than it might seem in many ways, especially when it comes to the simpler types. So floats, of course, are not necessarily simple, right? They are made up out of a complex relationship that has certain deficiencies and so on and so forth. We can't just take two F-32s, push them together, and now we have an F-64, right? But if we have 8 bytes, we can simply say, well, regard this as an int, right? That is a completely valid thing to do. Is it always going to end up with the result that you want? Maybe not, but at the same time, this is really not necessarily an issue, right? You can always just, this is why we can, for example, we can serialize an integer by just writing out 8 bytes to some place, right? And as long as the other side knows that this is supposed to be regarded as an integer, these 8 bytes, we are fine, right? But therein lies the problem, right? To some extent. When we serialize, sometimes we want to encode this. Sometimes the other side knows what it needs to do. And then we can have a very efficient transfer of this information, right? This is what file format and stuff actually usually are about, right? So the relationship between all of these values and how they are, how they look and so on, is important. And we can use and abuse this to a large degree, right? So let's say we have structs here. I'm going to say int bool struct here. We know we have our integers and our booleans here. Let's say we have a struct with 2 integers and 1 bool. Now the size of A here, this definition, is 24. That's not necessarily what we would expect unless we have some insider info or whatever here, right? Unless we have come prepared. The reason for this is alignment. And so memory access, just to kind of oversimplify here, is more efficient when we align to certain boundaries and so on. And in this struct here, the int is the largest thing. And so we will align to 8 byte boundaries. And so what we actually get is 8, 8, and then 8, basically. If we wanted to somehow not do this, which generally speaking, we shouldn't want to apply this trick here, we could say that this struct is packed. And for certain serialization formats and so on, you might actually do this. It depends entirely on what you're trying to do and so on. So a packed A is 8 for one integer, 16 for the second, right? So we're up to 16 at this point. We have these two, right? And then we have 1 byte for the bool, right? So this, and so we can have structs that are packed, right? But that doesn't necessarily always make a lot of sense. You should probably look at your use case if you want this, right? So I also want to take a look here at struct and transmute struct. So when I say that memory can be regarded as something and so on, I want to be very clear that I'm 100% saying you can take these 3 integers, right, and basically just transmute them into this A here. So if we were to say transmute, right, these 3 into A, we would get this. So just to kind of clarify here, this transmute struct here in reality, what we're doing here is this. Let's output that again so we can see very clearly. We're taking this and it becomes this. This is an array, right, of integers. That's all it is. Why? Because that happens to be the actual memory layout of this here, right? We can simply regard these three integers as an A. And because the sizes here match, that's why we can do this. If I were to regard these three integers as a packed A, we would get the compilation error. You can't transmute this. It's 24 versus 17 bytes, right? So it's not that this is completely without safety. It is with some safety, right? But at the same time, this is just simply, everything is just a series of bytes at the end of the day, right? And there's usually no actual productive point to not regarding it as just a series of bytes, right? So I'm not saying that we shouldn't use actual types and so on, right? We shouldn't just sort of say, well, since everything is just an array of bytes, why not just have everything be an array of bytes in the actual code, right? But we should understand that when we are looking at memory, what we're actually looking at is just a series of bytes, right? When we have a memory address to somewhere, this is really just an index in some sense to an extremely large array of bytes, right? They happen to be split into pages and so on by your operating system. But a page itself can be regarded as simply an array of bytes as well, right? So this struct is really just a sequence of values, right? The fields don't even come into it. These fields being renamed means nothing, right? It only means something if you want to kind of make some kind of generalized decoder for some type or something, right? Serialization might want these fields. Ideally, they probably shouldn't, right? But if you're making something generalized, yeah, absolutely. So let's look at unions also. We have two unions here. And unions are a little bit trickier, but once you kind of know some of the magic sauce, you can understand them fairly simply, right? So we have a union here. Let's actually output struct as well. So here we have our A struct, right? And here we have a union that contains this, right? And we need to remember that A is 24 bytes. So here we have byte and int, right? Our union is 32 bytes. If we were to remove A, we would go down to 16 bytes. So why is that? Well, the reason for this is because a union will take up the space of the largest member plus a tag value. That tag value resides in an offset inside of the structure. So that might not make a lot of sense, but we're going to take a look at some code that might make more sense, at least. So what we're actually doing here, when we remove A, we're saying, oh, now the largest size is 8, right? This int here. And then we have 8 bytes of tag value on top of that. And that's how we get to this, right? So you can basically, a good rule of thumb would be just union is the largest member, largest member's size plus the tag. And so if we look at a little bit sort of the internals here of Odin, we can actually see here, for example, if we have the set union variant raw tag, we can actually see how these values are actually created internally. So here you can see that there's a tag pointer, and we create a uint pointer, or rather, we calculate a offset, right? By looking at this tag offset here. And then we we set this tag value inside of this union. So if we look at type info, I don't remember exactly how it is. Type info union probably. Let's see. Actually, we can probably put 2 colons there. So internally in the actual compiler, or this is in the reflection machinery, I should say. It's not in the compiler. In the reflection machinery, we have these things, right? We can kind of derive some of the behavior of some of these things here. We're going to take a look at a practical actual application of this knowledge as well. But here we can see that we have variant, right? And these are all the cases we have. So in our case, that was a byte, an int, and an a struct, right? Then we have a tag offset inside of the type info structure, right? That tag offset points to basically where is the tag located in this data, right? And then we have a tag type that talks about what is the tag's actual type, right? We can surmise from what we were looking at that the union's tag was in fact an int in our case, right? Because we added 8 bytes on top of our other values, right? So int went to 16 because that's 8 plus 8. A went to 32 because that's 24 plus 8. Right, so we can surmise that it has to have been a tag of 8 bytes, right? So, like I said, how would you use this kind of practically speaking? There might be a little bit of insight we can get from a project here that I have. Let's see if we can, that's the wrong file. CLI.odin is the one I want, of course. So here we can first see that we are dealing with these union things, struct things, and so on. And I want to take a look at how we use this tag offset field. And please understand though that this is not necessarily something I'm saying, hey, you should do this absolutely everywhere, because there are certain downsides to regarding memory as just a series of bytes, but sometimes you either have to do it or you're not smart enough to come up with a better solution. I can tell you that I suspect that the latter is the case for me. This is the CLI package that I have mentioned in a previous video. And in this package, what I actually do is I simply construct a value from the type that you want decoded. We construct a series of bytes and say, here's the actual size of what I'm trying to decode. So make that many bytes. And then we basically say, construct that value in memory from what I have decoded. So as an example here, parse arguments with union CLI info takes our union CLI info structure here. All right, so we have a size and a tag offset and variant and start tag and so on. Start tag is actually basically, can we have nil or not? Then we basically say, okay, for every variant in our variants, get the struct decoding info. That's how do we decode each struct inside of this union, and so on. And get the name of it and see if we can find that to decode, right? So if the first argument is this name of that structure, we want to say, hey, here's the actual variant that we have. So the variants are ordered. They start from 0 and move along, right? So they're 0 indexed. And here we say, okay, the tag I have is this number. So we can see this is just an int, this variant tag here, right? And then we say, copy that into our tag offset. insert that into the position where tags are stored in this union, right, in the bytes. And then we parse the struct, right? We saw structs are really just, you know, a series of bytes that contain whatever information is happening in that structure, right? So for example, here we say copy the value byte from 0 and forward, or copy into 0 and forward the payload bytes that we have gotten from this parse argument here function. This returns a slice of bytes, right? And we copy that slice, the contents of that slice, into our value bytes. And then we return that from this function. And that function will then, if we look at how this is being used, we can see here bytes remaining, right? This returns this slice of bytes. Here we say, regard this reinterpret copy as a T. So this function is generic, and a T here will be whatever type you're trying to decode from your command line app. And then we get the raw data from the bytes that we have, meaning the actual underlying information. Regard that as a T, right? That's what this line does, and then it returns it. And of course, the user does not see this, right? But this is effectively abusing or using the fact that structs are just sequences of bytes. Unions are basically a tag plus some data. And that data has to be for that tag. That's really it. If we then use the reflection machinery, right? So here we can see, for example, we can get the struct fields in something. We can get this union, we can get union variants and so on, right? We can get these this neat information about unions and so on by doing a lot of this stuff and so on. So everything is just a series of bytes at the end of the day, right? And if you are having a problem, for example, it can be useful to simply say, okay, back to basics. I have a series of bytes. What do, right? Again, I'm not saying this is the solution to everything, but it's also something that you just should keep in mind. At the end of the day, there are no actual types at the end of the day, right? We use them because they happen to explain much more clearly, in many cases, what is actually happening, what we're expecting. Well, I have an int, that means I have a series of 8 bytes together, regarded as one number, right? That is a very useful thing to say. But it's also very useful to understand that this concept doesn't have a lot to do necessarily with what actually exists in the data, right? I should also note, by the way, that when we look at int here, so when we look at int and uint, it's not actually the case that these are always just 8. What actually is happening with int here is that it's register sized. So if you were running on a 32-bit platform, for example, it would be 4 bytes, right? So it would be an i32. And yeah, that's just how it is. And this is, you should, generally speaking, just default to using int because it is register based. This will interact very nicely with a lot of things. It will be reasonably fast and so on. And we know that it fits in a register and so on. So that's it for talking about types and data and so on. And I hope for those who might not be used to these things, I hope this view of structs and unions and composite types and arrays and so on. Actually, I forgot to mention arrays. Right, so we can see here arrays, by the way, actual arrays with a known size are literally just a sequence of that thing. So 2 integers become 16, right? 2 i32s is just 8. 2 bools and so on and so forth, right? These are very straightforward. When it comes to slices, however, right, a slice is really just a view into an array, right? So this is the actual definition from Odin. Raw slice here is a struct with a pointer to some data and a length, right? All slices are the same size, right? That's because this here is 8, right? A pointer, it's pointer sized, right? Which on 64-bit machines means 8 bytes. Likewise, we have our int, which is register sized, which on 64-bit machines means it's 8, right? So here, what you actually get is just 16 for all of them, right? If you have a dynamic array, we have yet more data, right? And so we have data, which is a raw pointer, we have a length, we have a capacity that is stored, and then an allocator, right? So here we have, 8. Actually, allocator is interesting. Let's take a look at this might be interesting. So we have 8, 24, and then 16 for the allocator, I suppose. Yeah, the allocator has to be sized at 16. Let's briefly just take a quick look at that. So array, let's just say printf allocator. Let's just sort of output this. Yeah, so the allocator is 16, right? And this makes a lot of sense, right, from what we have looked at. Importantly, again, dynamic arrays are all the same size, right? You're not going to save space by having something different. Of course, you're going to save space somewhere, right? This data points to somewhere, right? But storing the slice, it means nothing for storing the slice reference, right? And so on. Arrays are straightforward. They take up the space that they take, right? There's no more information. It's just a series of bytes. The slices and dynamic arrays are references to somewhere, so they store reference-sized things, right? Raw pointer, and then they have the length, which is an int, and so on. So yeah, anyway, now finally we are actually at the end. I just wanted to kind of show these things because I'm not entirely sure that everyone who watches these videos or will in the future actually is kind of, that they actually kind of know these things, that there's no such thing as field names in actual raw data. We can construct these values in just about any way we want, really, because we have the freedom to do so. We can transmute one thing as another, and it makes sense still somehow, right? And I just wanted to kind of highlight these things. If you like this type of content, of course, this is a little bit more basic, maybe, and so on. If you like this, please speak up. If you have some feedback on it, absolutely just comment. If you want more stuff like this, please subscribe, and yeah, have a nice day, and ciao.